Hey there, this is video PR14, and we're going to talk about the add formula for probability. And this specifically talks about two things happening. It's not when you have the overlap of two events and then you're finding the intersection part. This is one thing happens and then another thing happens. So slightly different, and that's why I underlined, highlighted, scribbled around the idea of its two actions. Suppose a coin is tossed and a die is rolled. Draw the sample space to show all the probabilities. So I'm going to draw a tree diagram. So there's my start. If I toss a coin, it's either going to be heads or tails. And then if a die is rolled, 1, 2. Okay, the tree diagram isn't going to look that great. 1, 2, 3. I didn't get any better. So here, let me do this. Heads 1, heads 2, heads 3, heads 4, heads 5. There's my sample space. And I knew it's correct because we have 12 of them. And if you go back to the fundamental counting principle, there's 2 choices with flipping a coin, and there's 6 choices. So 2 times 6 is 12, and I know there's 12 there. Okie dokie. Now, determine the probability of tossing a head. So there are 6 times I got that. Or instead of looking at the whole sample space, you could just say, well, there's 2 choices and heads is 1 out of 2. Either way, you're going to get a half. Now we want to roll a number less than 3. So I'm going to do this. Remember, it said less than 3, so 3 is not included. So that's going to be 4 out of 12. I think that's 0.3. Repeating. Oops, no, I did that. Or again, you could have thought of just the die. There's 6 sides, and 1 and 2 are less, 2 out of 6, which takes you back there. It doesn't matter. Now, this is where the AND formula comes in. It's 2 things, one happening first, you roll a number less than 3, and then you toss a head, although I notice I did flip my order on that. Oops. And if we count here, then the only ones are going to be those 2. So that's going to be 2 out of 12, which is 1 out of 6. And I don't know what that is. Oops. Oh. 2 divided by 12. It's going to be a repeating decimal. 0.16 repeat. All right. So what is the relation between the first 2 answers and the third one? If you take 0.5, you multiply it by 0.3 repeating, you will get 0.16. At least I sure hope we do. Let me see. 0.5 times Oh, you can't see that. Move that up so you can see better. And yes, I put in all those 3s for fun. And then we get our number. So, and that's our formula. So you have 2 events, and these are, nope, It'll work all the time. I guess the only thing I have to say is pay attention to that second event. Sometimes what happens in the second event will affect, what happens first will affect what happens second, which is what I'm going to talk about now. All right, however, you need to be careful as the probability of the second event can sometimes be dependent on the probability of the first one. So either depends or it doesn't. So in independent events, what happens the first time does not influence what happens the second time. And we have dependent events where what happens the first time does influence what happens after. Which sounds really complicated, but once you see the examples, you're like, oh, that's what she means. All right, a drawer contains 3 red paper clips, 4 green paper clips, and 5 blue paper clips. 1 paper clip is drawn from the drawer and is replaced when the second one is drawn. So let's see, you've got grand total of, you got 12 paper clips. You take one out, whatever color it is, and then you put it back when you draw the second one. Well, by putting it back, you've essentially got, you're back to the very start. So there is no change in the probability. So these are independent events. Maybe it's easier if I explain what a dependent event would look like with this. Would be exactly the same question, but you take the first one out and you don't put it back. Well, if you remember, when we started, there were 12 paper clips. Okay, and you got the probabilities for each of those, whatever they are. But the moment I take 1 paper clip, that's going to change my sample space. So what happened the first time did affect. All right. I'm getting a little off track, so let's go back here. Being late and getting the look from your instructor. Yes, those 2 things are connected. At least in my class, they sure are. All right. So you are more likely to get the look from me if you're late than if you're just walking in on time or even early. All right, drawing names, marbles, and hats. Oops, drawing names, marbles, or numbers from a hat with replacements. So what that means is, say we have a bucket with 100 numbers in it. Oh, let's make it more exciting. It's a raffle and your name is in there once with 99 other people. So there's 100 choices altogether. So if I pull your name out, yay, you win the first thing. And then I put it back, next time around, you've still got the same chance of winning. So those are independent. However, if you did the same thing, and let's say I pulled your name out again, and you only, by the way, you only have 1 ticket in my example now. So you had a 1 in 100 chance the first time, you have exactly a 0 in 100 chance the second time. So what happened first affects what happens second. So these are dependent events. Generally, if you take stuff out and don't replace it, then it's going to be a dependent thing because it's going to change your sample space for sure. Sorry. It might change the event, like it might change the top number, but it's definitely going to change the pool that you have to choose from. Okay. Now, by the looks of it, there is another page. All right. Wow. Getting it raining, given that it is Sunday. Sunny or cloudy. Not really sure what I was trying to say there. Getting rained on there. Well, that's going to depend. If it's a sunny day, you would not expect to get rained on. Or if it's cloudy, you might expect. So those depend on one another. So that's a dependent event. Okay, I pick Dave, given that I've already said I've picked a male from the class. Well, you got a class to start. I guess I'm making the assumption there that it's your average class. You got some males and some females in there. But the moment I say, hey, I already picked a guy, all the girls are like, oh, I'm not part of the choice, not part of whatever this draw is anymore. So I've changed my sample space. So that makes it dependent. picking an ace from a deck, given that I've already picked a 2 and replaced it in the deck. You know what? You should stop the video. You should try these last few questions. All right, I'm going to trust that you did that. All right, so there's 52 cards. I picked out a 2, then I put the 2 back, and now I'm going to pick an ace. My sample space hasn't changed. I'm back to the original deck of cards. So that's going to be independent. Picking 2 cards from a deck without replacement. Well, there you go. Right there is telling you it's going to be a dependent event. So I got 52 cards. I pull out 1, whatever it is. My sample space is now changed to 51 cards. There's less. If I pull out another one, it's going to change to 50. So my sample space is changing. So my probabilities are changing. If I picked a card and put it back, and it was 52 across, all the way across the bottom, then it would be independent. Oops. The probability that I get sick, given that my children are sick, oh goodness, we all know that as parents, that's dependent. Doesn't always happen, but it's certainly more likely. Our little lovelies bring all sorts of fun stuff home from school. All right, probability that the next card will be an ace, given that the dealer is showing 13 and I have a jack in my hand. Well, I'm not sure I like that question, but I'm pretty sure it depends on it. I'm feeling that's dependent. Simply because I'm thinking there might be an ace in here somewhere. I just don't think I should have put that question there. Shh, don't tell anybody. All right. There might be different answers in the answer key because now I'm going to second guess myself. Okay, let's do the questions and see where we go here. Oh, look, it's a paperclip question. A drawer contains some paperclip. One paperclip is drawn from the drawer, is replaced, and the second one is drawn. Here we go. What is the probability the first clip is green? Okay, so 3 and 4 and 5 gives me a sample space of 12. And I want to know green. So there's 4 green ones. That's my first event. Now I'm going to multiply that by my second event. However, it says we replace the paperclip. So that means we're back to the beginning. So there's 12 there. And the second one being blue is going to be 5. And then if you remember, you multiply across the top, 20 out of 144. That's going to give me 0.14. It's actually 138 repeating. There's my answer. Okay. Number 2, how does the question above change if the first paperclip is not replaced before the second one? All right, so the first part's still the same. There's 12 paperclips, and we're taking a green one. But if I do not replace it, then there's going to be 11 paperclips left. And there's still 5 blue ones. So, make sense? Right? And this is going to give me 20. Don't laugh at me. 132. 0.15. That should make sense to you. It should be slightly higher, right? Because I took that green one out. There's less green, there's less paper clips, there's less to start with. So the ratio of like the blue ones to the whole thing is going to be higher. Okay. 2 more questions and then we're done this video. Numbers 1 to 13 are written on slips of paper and a slip is taken out. Oh, there's what I'm looking for, not replaced, and another one is taken. Oh, this is hard. Okay, I shouldn't have said that. It's not hard. I'm just lazy. I don't want to have to think about it. So my sample space is 1 to 13. Ta-da! I wrote out my sample space. Okay, so first one, there's 13, and I want to know if it's odd. So 1, 2, 3, 4. Now, I don't replace that. So that means whatever I picked, there's now only 12 slips of paper left. And let's say I picked the 1, and that's going to leave me 1, 2, 3, 4, 5, 6. And that, my friends, is why I wrote out my sample space, because otherwise I'd have to think a lot harder to get that answer. All right, that's going to give me 42 over, I don't know, 13 times 12, 156. So it's going to be 0.269, so 27. I'm rounding to 2 decimal places. Okie dokie. Now, we want the first one is even, the second one is odd. So 13 to start with. Pretty sure the answer is 6 here, but I'm going to count 1, 2, 3, 4, 5, 6. There's 6 even numbers. Times, we didn't replace it, so this is going to be a 12. Now we want odd. 1, 2, 3, 4, 5, 6, 7. There we go. So 42. Oh, that's weird. I thought it might be different. Same answer. Yeah. And there we go. End of the video. Have a spectacular day. Remember, math is not a spectator sport.